Hello, in this video let us try a few numericals on projectile motion that we had studied a few uh, videos back. Now we are considering, let us suppose we have a question which says that we have two bodies that were thrown simultaneously from the same point, one straight up and the other at an angle of 60 degrees to the horizontal. So we have two objects over here, one of the objects over here and the other object over there, and this object is probably projected with upwards, and this one at an angle of 60 degrees with respect to the horizontal. This is the uh, velocity vector. Obviously it will take a parabolic trajectory as expected, but this angle with respect to the horizontal is simply 60 degrees. Now what do we have, or what do we have for us to calculate? The initial velocity of each of the body is just equal to v0, which is equal to 25 meters per second. So this is projected at 25 meters per second along that line, and this one obviously is also projected at, let this be v dash vector, because it is directed in some other direction, and this is v vector which is directed straight up. This is also 25 meters per second. Now both the velocities are 25 meters per second. We neglect air drag. What we want to find is the distance between the bodies at t is equal to 1.7 seconds later. We want to find the distance between the two projectiles at t is equal to 1.7 seconds later from the time that they were projected into that space. Now it's quite simple to approach. Now here in the first case, let us take the example of the body that was projected straight up. Now the only displacement that we can expect is along the straight line in the vertical direction. So let the displacement in the y direction be y1. This is the first body, and let this be the second body that we are considering. Now for that, y1 is the displacement along the vertical line, and so that can be given as from the equation of motion, s is equal to ut plus half at squared. But in this case, y1 is the displacement along the vertical direction, which is against the gravitational force, though you have the velocity initial to be equal to 25, and the time that you are obtaining it for is 1.7 seconds later, and obviously you have the acceleration to be negative. I'll write it over here. So this is half times of minus 9.8 because of the negative acceleration acting downwards. That is the acceleration due to gravity g, which is 9.8 times of the time squared. S is equal to ut plus half at squared, plus half a is negative in this case for vertical motion. Now along the x direction, obviously it doesn't really make any sort of movement along that line. Now consider the case, this is the case for the first body. Now consider the case for the second body. Now for the second body, as it travels with a constant speed along the x direction, and so it will travel a distance of x2 along the x direction, and that too with a constant speed, which is 25 cos theta. Now cos theta, that is cos 60 over here, is simply equal to cos 60 equals half. So that is the speed along the x direction, and obviously you have the time which is 1.7 seconds. So this is the movement with no acceleration involved because the air drag has been neglected. So that is the movement or the displacement along the x direction for that body. Now the movement or the displacement along the y direction for that second body, which is projected at an angle of 60°, you have the sine component of it to be acting along the vertical direction, as we had discussed in our theoretical video. So this is 25 sine 60, which is √3/2. Now this is the velocity along the y direction, but we are to find the displacement at time t is equal to 1.7. So we proceed in the same way that we did for this case as y1. Here only the velocity instead of 25 is a component of it. The rest of the things are obviously the same, that is plus half of minus 9.8 times of 1.7 squared. Now in order, obviously you have the displacements of each and every coordinate, displacement along each and every coordinate for this, and from that what you can obtain is the displacement over here, the relative positions of or the distance between those two bodies. So how do we do that? We just apply coordinate geometry, and in that case what we do is we just take the, here r will be equal to x1 minus x2, that is the displacement along the x direction, squared, plus y1 minus y2 squared, right, and each of it under root. So simply coordinate geometry, because let us say that they were projected from the origin at 0, 0. One of them went to a distance of y1 with x1 0. So you have 0, y1 as its coordinate after reaching this point at 1.7 seconds, and the other fellow who was thrown at an angle of 60°, maybe that has reached somewhere over here, let us say, and it has a coordinate x2, y2. The distance between them is obviously this line which connects them directly, and that line can be obtained just by coordinate geometry calculation, which involves this relation. School stuff. Okay, so from that we can obtain this value. We have the values, we just need to put them up. Now x1 is 0, x2 is this value, 0 minus that, again squared will give you a positive result, so we keep it as such. 0 minus 0, this goes to 0, this is 0 minus x2, x2 has the value, but again negative when squared becomes positive, so we just keep it like that. 25 times of half times of 1.7 squared completely, plus y1 minus y2. Now in this case, if you have the second terms, as you can check for yourself, they are the same. So if you subtract one of the terms from the other, the second terms do not count, they cancel out right away when we are subtracting one of the terms from the other. We put a minus sign in one of those terms, so minus of minus becomes plus when taken from that, added to the other term, that gives you a 0. So that is not our problem. So here the thing that y1 minus y2 has, it has a certain it has some common things to deal with, that is 25 into 1.7, 25 times of 1.7 minus 25 times of 1.7 again, 25 times of 1.7 once again, multiplied with √3 divided by 2. So what we can, and obviously that is under that is squared, and all under the root. Now if you observe the second term over here, what we can have is 25 times of 1.7 can be taken as a common value. In fact, we can take the 2 out of it as well, and here in the bracket what we have is the 2 goes as LCM, so 2, and this entire thing has been taken common, so what we are left with is just root 3, and root 3 divided by this entire thing divided by 2, and that again is squared, which uh, is the case with this first term as well. Now if you once again observe closely, this value squared is completely similar to this value squared, so again this can be taken as common. So that taken as common in this case has 25 by 2 times of 1.7, that was squared, but now that has been taken as common, so common out of the root, so the root has acted on it and we have just the number. And here under root, what do we have over here? We have 1 squared, obviously, plus this term. Now this term is having the value, the 2 has gone outside, the 2 is not there anymore, so you just have 2 minus root 3 squared. Now 2 minus root 3 whole squared is just 4 plus 3 minus 2 times of 2 root 3, that is 4 root 3. That seems pretty clear. 25 divided by 2 times of 1.7, and this is simply 8 minus 4 root 3. 8 minus 4 times of root 3 is approximately 1.732, as we know, so that is 6.928. 25 by 2 times of 1.7, 8 minus 6.928 is 1.072. 25 by 2, 1.7, 1.072. Now had we got 1072, that would have been a different thing, but this is 1.072, which has a root value of nearly oh, it has a value of nearly something, let me calculate that separately, and that comes out to be nearly equal to 1.0353, something like that, and that when multiplied with 1.7 and 25 by 2 approximately results in 22.001, something like that, which is nearly equal to 22, of course. So this in meters is the distance. Now although we have obtained the value, which is absolutely correct, we can have a separate approach. This is a pretty straightforward question. We will be dealing with different questions related to the topic, especially in straight line motion, where it will be easier for us to consider the case of relative motion. Here also we have relative motion to be involved in this case when one of the objects shifts away from the other object. Obviously it is moving along a relative line over there. So let's check that in the other way, uh, in other possible way, which will be more easier, not for this, but this is this method looks easier, not for this, but for some other method, for other type of questions which involve uh, some serious calculation. Let's check that out once again. uh, before really moving over to that, let me give you a theoretical approach to it, or an idea, a brief idea of what we are about to discuss and the related equations that can possibly come into play. Now here, suppose we have an object to be moving along a certain line, and it has an initial velocity, suppose of v01 for the first object, and then we have another object which probably has a velocity starting from the same point as v02. That is its velocity. Now these are moving at constant rates, or let's say that they have an acceleration. Okay, let's take the accelerated frame as a whole. Now, had there been no acceleration, what would have been the case in the first instance that I was just saying before this, that this was probably at the relative distance. There was an initial relative distance between them. If they are starting from the same point, the relative distance between them, that is r0, that is a position vector which is separating them, r0 of 1 with respect to 2. Because I have taken the starting point to be exactly the same for both the things, obviously this thing goes to 0, but this thing would have been some finite value had we started off like this. Means it would have been at a position over here, it would have had a separate position with respect to a given frame over here, and then we would have had a relative position between them in this case as well. How do we know the relative position? Now, the relative position obviously is r012 that I've written over there is simply in the vector form r01 minus r02, which is the case we had discussed in the relative motion. So this is the relative position between them, and how do we get that over here that I have just said in this figure? Now, if suppose we have an object over here, we have another object over here, then this is r1, or say r01, and this is r02, and from that the relative position, as I say, r01 minus r02 will be simply this one, because r01 plus this relative position that I am saying, r01 with respect to 2, right, that falls in place, because sorry, this is the other way around. This is from the triangular, that r02 plus r012 is r01, right? And so we have r012 to be equal to r01 minus r02. This is obviously the relative case which is given by this, and the direction obviously points between those 2 points where the relative position is being obtained. So in this case over here, the relative position is obviously 0 because they are starting from the same point, which is exactly the case that has been given in the question that we just discussed prior to this. Now, as these travel along with time, they with the velocities of course available, v01 and v02, along those lines, as they travel, they have a relative velocity between them with respect to the time. That means if I am to consider the relative distance now after a certain amount of time, that will simply be equal to the relative position initially plus the velocity that they have developed relatively, and this is, remember, the initial velocity multiplied with time, because these two are giving distances, right? And how is that possible? Well, in this case, if you look at this figure over here, again the relative velocity in this case v012, is simply V01 minus V02, and as you just found out over here, that is R012, similarly you will have V012 to be acting along that line, which the magnitude of which is giving me the relative velocity in that given time, in that case, right? So now this thing is the case when we have no acceleration, but in case of an accelerated frame, in case there is a relative acceleration between those two objects, suppose one of them was accelerating at a certain rate and the other one was accelerating at another rate, then we would have had an additional half a12, that is the relative acceleration between them, multiplied with the square of time. Now this equation that you see over here is very influential in solving a number of numericals quite effectively. Uh, this is somewhat, or if not exactly, similar to the equation where you have S is equal to, instead of S you have R is equal to ut plus half at squared, isn't it? Now this is exactly the case, but this case involves relative motion because we are involving two objects and we are obtaining the relative position with respect to the variation of their motion with respect to time. So here, instead of ut only, the change that you experience is this complete thing, which is quite analogous to ut, because that ut gives distance, so that thing is giving distance as well. Now now we move back to the numerical that we just discussed. In our question that we discussed right now, one of the projectiles was going like this, the other one, this is the particle 1, moving at 25 the speed, if you remember correctly, just a few moments back, and this is the trajectory, because this is 60 degrees with respect to the horizontal, and that too at 25 meters per second projected initially. Now this motion that we discussed over here as an example, we were considering that on a horizontal plane, because obviously we had taken the example of two objects moving with respect to one another, let's say on a road, so that was a horizontal plane. This is also a planar motion, but the plane here is vertical, and in case of vertical motion there is a certain acceleration which is acting, and that is the acceleration due to gravity. So you can probably expect an acceleration term to be finite over here that I had just mentioned, a12. Let me write that clearly for you once again. This is half a12 t squared, a12 being the relative acceleration. So you have an certain acceleration over here, but what about the relative acceleration? Well, the relative acceleration in this case will be 0. Why? Because the the projectiles that are fired, they are under the same accelerated frame, that is the gravitational acceleration only, because along the horizontal line you do not have any sort of acceleration, as we have been discussing time and again. There's no air drag, the air drag has been neglected. So what we expect over here is that the only acceleration that is acting simultaneously on them is equal for both the cases, and that is the acceleration due to gravity. And with that acceleration being the same for both of them, the relative acceleration between them obviously goes to 0. That means a12, that is the relative acceleration that we had just put in over here, that goes to 0. So the above equation, in this equation, if we put it over here, what we get is it becomes very easy now to solve. We have we had r0 1 2 and we had it to be 0. We have v0, 1, 2 in a given time, and we have half of this one obviously is the ut term, and we have half of the relative acceleration times of t squared. Now the relative acceleration has taken a backseat as well, that is 0. So now the relative position will be pretty easy to determine. But for that, we will have to consider the relative velocity. Now the relative velocity in this case is obviously v1 minus v2, v01 minus v02, v0 being the velocity, initial velocities. So v01, this equation that I have at hand is a v01, I write it vectorially, v01 minus v02 whole multiplied with t. But again, this is vector, and the angle between them, as you can see, is 30 degrees, but definitely you are considering this second vector in the opposite sense because this is negative of that vector over here. So this is simply, as I have time and again discussed previously, this is v02 minus plus of minus of v02, and that multiplied with the time. I need not write it once again, but I just wrote it for your better understanding. So we have v01 squared plus v02 squared, and in case of relative motion we have 2 times of v01 v02, and the angle that was between them, that is cos 30 in this case, because in positive directions the angle between them was 30 degrees. So cos 30, and that all taken under root, and that finally multiplied with t. This is obviously the magnitude of it. Now this is 25 squared, the other one was 25 squared, minus 2 times of both being 25, we again have a 25 square term. Cos 30 is simply root 3 by 2, that under root multiplied with the time, that is 1.7. 25 squared, 25 squared, 25 squared can be taken common. All that remains within the root over term is simply 1 plus 1 minus 2 times of root 3 by 2. 2's get cancelled. What we are left with is 2 minus root 3. 2 minus root 3, this is 25, and this is 2 minus root 3 is approximately 0.134 root over 1.7, and if we calculate this one, it's actually the double of that, that is 0.268, and that equates 22 as well, nearly 22, 22.0017 or something like that. So that is 22 meters as well. Now, although the explanation part for your understanding involved this entire thing, but the equation that we used is simply this. We discussed this entire thing for obtaining this expression, and after we have obtained that expression, by knowing that expression, you can just use it directly to obtain any sort of relative position between two objects which are set to motion, and even if they have a certain acceleration which varies with time, sorry, a certain relative acceleration in that time, you can put the value for a12, which was 0 in this case because of the common gravitational force, and you can obtain the result quite easily, I hope. Now, as you have watched this and probably understood a bit about relative cases, I would leave you with a question which I'll be solving in the next video. uh, but you can try it for yourself. Now, the next question carries that if I have two particles to be moving under uniform gravitational field with which is under the acceleration g, and at the initial moment the particles were located at one point. These are the two particles, they are located at one point, right? And they move with velocities, let's say 3 meters per second and 4 meters per second, but in horizontally opposite directions. And they are obviously uh, moving like horizontal projectiles under the gravity, because the question starts off with two particles moving in a uniform gravitational field. So they are certainly at a height, and they are just initially starting off from this particular point over here, and from that point they are moving in opposite directions horizontally. And as they move horizontally, obviously they are going to have a certain trajectory like this for this particle and this for this particle, right? And after some time they will probably be at mutually perpendicular lines. They will be at mutually perpendicular lines, just like in the case over here. I'm leaving you with the figure, which will be easier for you to understand. Probably this is over here along this line, as it is taken backward from that point over to here, and this has reached this point, let us say, and from this point if you take it backward along the line, then you have them to be at right angles over here, right? You need to obtain the distance between these particles at that moment when they are at mutually perpendicular angles or mutually perpendicular directions with respect to one another. So this is your question. You have a brief idea about the motion and the relative motions involved. You can use that, or you can just use your skills on projectile motion and try this numerical. I'll be solving it in the next video, but till then, thank you for watching.